So today we start on the background theory behind the finite volume method. And the book we are going to peek into is the one by Versteeg. It's an OK book. It's a little narrow. It doesn't cover, say, the area of CFD very well. It focuses on one method, one way to do things. Luckily for us, that's the same way they have done it in the OpenFOAM. So it's sort of the OpenFOAM background manual. But it doesn't really take the entire area into account, but it's definitely the most important part when it comes to CFD codes. So I will not go through this book page by page, of course not. I will start by giving you a sort of an overview over CFD, which is not in the book actually. Then how to obtain the equations. And today I think we also can start with the turbulence part. How many here have taken this turbulence course that is given by Helge Andersson? One? Only one. The rest, have you taken any turbulence? You have been taught turbulence a little bit at least? Yeah. And some of you have never touched on turbulence. Yeah, okay. So you have all kinds. Never mind. Let's start here with an overview. Of CFD. CFD, so you should have learned by now, CFD is computational fluid dynamics. Also sometimes colors for directors, because it's very easy to get very fancy plots, nice colors. Then you go to your boss and ask for more money on your fancy project. Colors for directors. We have several ways to do this. What we have done so far is a Taylor series expansion or formulation. Taylor series formulation. This is what we call finite difference. So this is the Sula algorithm based on Taylor series. You construct recipes for the different derivatives, insert them into your partial differential equations, and end up with a set of algebraic equations that has to be solved. Second, we have something called variational formulation. Variational formulation. Now we are talking finite element. This is based on minimizing the corresponding functional. A functional, I guess you haven't had enough math to understand this. I don't think you have a variational calculus. It's rather heavy mathematics. You see the teacher jumps into something called the Hilbert space and never surfaces again, so the students never understand what's going on. It's really hard math. But here it's actually where finite element started. That's in solid mechanics. very heavy math, very hard to understand what the heck is going on, and finding the corresponding functional to be minimized, that's a heck of a job. I haven't even seen a complete functional that then should cover the entire Navier-Stokes. So doing it this way, from a poor variational formulation, very hard when it comes to fluid mechanics. More for the solid mechanics. Finally, we have the method of weighted residuals. Weighted residuals. So here in this family you find both finite element and finite volume. So you have your PDE, partial differential equation, one or several, and now I'll just write them on the form L of an unknown phi equal to 0. So this is a PDE. This L will now be a partial operator. So it would be things like ddt plus velocity ddx, yada yada yada. So we just write it for short. An operator, insert now an unknown, which can be anything, pressure, velocity, whatever you want. Just to get it on the form equal to 0. This will now be the correct analytical solution. It's identical to 0. We don't have an analytical solution. We will have our approximative solution. So we have a phi mark, phi bar or something. And we express him typically with as a series A0, A1x, A2x square, whatever. So he's sort of given by a whole bunch of coefficients and some distance here in a range. And if you now insert this approximative solution into the correct partial differential equation, you will get a residual. You will get something that is different from 0. So here our residual, C dual, which we now wish to make as small as possible, to be minimized. We now introduce a weight function. A W, and then we write it on the form oh yeah. we write it on the form the integral of the weight function multiplied with the residual over an area, or actually a volume, say volume, equal to 0. So this is how we are going to work, and how to obtain this one close to 0. Well, we are searching the best coefficients AI. Since you have the equation equal to 0, you can of course do whatever you want here. You can multiply, you can raise it to the power or whatever. You can play around with it as much as you like, since, well, you have 0 on the other side anyway. So who cares? So this one, we sort of treat him now as a piecewise continuous function. And we are now searching the coefficients to make this residual as small as possible. This volume, the entire computational domain, is split or divided. Divide the domain into small control volumes. And now we let W equals 1 whenever you are inside your volume, and then 0 elsewhere. So we sort of simplify it. W equal 1 inside the volume, and W equals 0 elsewhere. Then we are left with this equation here, integral over a control volume by only the residual alone equals to 0. So what happened now to finite volume versus finite element? What should we call this method? Some people call it the control volume formulation. Actually a better word. Control volume formulation. That's one view. The classical way will now be the following. If you do it as simple as this, just let this weight function be 1 when you are inside your volume. Then I will talk about finite volume. So here it's a very simple description, finite volume. If this weight function becomes more complex, then we're talking about finite element. Also, it's a question, how complex can your unknown be inside the volume? So say you have a volume here. Inside this control volume, you have your unknown phi approximative inside there somewhere. How can he vary inside this volume? So typically here, the easiest way, you will have one single value for him maybe in the center, and then you say he is constant inside this volume. Constant. Okay, clearly very simple finite volume. Sometimes we will say he can have a linear variation inside here. So if this is in the xy plane, you can say he is ax plus by plus c, a linear function. It's still finite volume. If he is more complex, if you have, say, a lot of, not just one single point, but you may have many points inside here, and quite a complex function, how he can be described inside one single volume, then you are talking finite element. So that's where I differ between finite volume and finite element. But you see they're very close indeed. So you can get the same expression, the same codes with finite element based on this residual formulation or the control volume formulation versus 0.2, the one that I called variational formulation. The code can actually be identical, but then it requires typically quite complex behavior of your unknown inside one single volume. Quite sophisticated actually. So then you can have rather big volumes and still have a lot of change inside one single cell. Remember in Solar, okay, you had one velocity, one pressure inside one cell. Here then you can have 20, 40, I don't know, a lot of different points inside one single control volume. Okay, just an overview there. You will have you have other methods as well. We have something called spectral codes, quite complex. You express your approximative solution here by a complete Fourier series. Then the variation inside one single volume can be very sophisticated indeed. And we have some mathematicians here at NTNU working with this. They call it the control volume spectral, finite element spectral method. So they mix it a little bit. Very complex description, very hard to understand for normal people, but it's actually quite efficient. They are getting quite strong. But for us, simple description, weight function is 1, and the variation inside one single cell is either constant or linear, no more advanced than that. Any questions so far? Okay. When you divide up your computational domain, the area, into small volumes, how do you do that? According to the background here, it's actually no rules at all. You can do whatever you want. So you can say here I have a control volume, CV, and here I have another one, and here I have a third one. And now these volumes are now part, say, in the middle of a stream or whatever. So yes, it would be possible actually, but not easy to solve it like this. Here you have an overlap region. Okay, we need some interpolation. Clearly these two have to talk to each other. This one is not really coupled with these guys, so very hard to describe it if this is in the middle of a stream. So the flow goes something like this. Of course, this is a bad idea. It would be very hard to do, but it would still be possible. Yes, you could do that. And then solve or try to find a solution inside these 3 volumes here. Naturally, what you do is to create volumes that is nicely patched together like this, so they are side by side. And why is that? Well, when you have, like here, influx and outflux through the side, the control surface, then here you know if anything that goes out here will enter into the next volume. Then you have better control of the transport properties here. When fluid moves from one cell to the next, or momentum moves from one to the next, then very easy or much easier to control it, to get it correct. So typically what you're trying to do is to let the cells be, say, face to face. But you don't have to. This would still be possible. Sometimes we will have problems where you have, say, moving parts. It will then still be possible to, say, construct one mesh here, and then you have another mesh, say something like this. And now, as time goes by, the red mesh moves differently than the white. So clearly, okay, now we are talking a lot of interpolation here to find a solution, but it will still be possible. So yes, you can have a lot of overlap between these volumes. That's still possible. So don't limit yourself to anything. This, of course, not funny. You don't like this, but still possible. With moving meshes, that is typically when you have, say, a moving part. You want to simulate the flow around, say, a propeller. He rotates. How do you do that? Well, you construct one mesh that is circular. So here you have some mesh system around the propeller, and then outside here you have a steady mesh that doesn't move. So now the inner mesh, he will sort of slide against your steady mesh, and then you will have to let these faces here, they sort of slide against the other volumes that doesn't move. Of course, a lot of interpolation here as well, and you have to sort of remesh for every time step. But better than this overlap thing. So here they will still be face to face, although one mesh is moving. See? Okay, more of this later. But for now, think of this as the way we are at least trying to do it. But don't limit yourself. A lot of things is possible. A lot of things may work. Okay, let us have a peek at the book. What is CFD? How does it work? And so on and so forth. So the first chapter, fairly easy to read for yourself. The conservation laws, that is something we should have a better look at. So let's have a, what is CFD? Yeah, this one we have started. Here you are talking a transport equation. So, I mean, somewhere you have to start how to find your equations, how to find the Navier-Stokes, you might say, or other transport equations for that matter. So you could have started here. If you have any unknown function, the rate of change in a control volume equals, then you will have some increase inside the volume, something that may produce this quantity. And then you have diffusion mechanisms. And then you will also have convection. Yeah. Production, convection, and diffusion. So a transport equation for any quantity, you can actually write it like this. ddt equals, what do we start with? We have convection. Convection. Well, actually, that one has been covered already now. It's inside here. But we are talking a diffusion. And then we have creation. That's production. And also what you should have is something that destroys it, minus a dissipation. So this will be more a typical equation. So he's missing the destruction here, so something that destroys this quantity. And now it's a question of modeling, how to find these different terms. So for the Navier-Stokes, yes, we can sort of identify these terms and have correct analytical expressions for them. For other equations, then we can start here and start modeling. That's also an option. Also, it's a question, here it's written in a differential form, but maybe we should have written it in an integral form, the volume. So have each term written as a volume integral. Maybe that would have been better. We'll see. Conservation laws. So typically, yes, here is the place we start. The mass is sort of constant. Conservation of mass. Of course, we have conservation of mass. If continuity equation is not fulfilled, then of course this is rubbish what we are dealing with. Then we have the momentum, the second law of motion. People often call it the conservation of momentum. Don't do that. The momentum is not conserved at all. What does Newton's law look like? Sum of forces equals the change of momentum, mass times velocity. So it's not a conservation law. Conservation law, that would be Newton's first law. Then you have no change of momentum. So don't call it a conservation of momentum. Call it Newton's second law of motion, then that's what it is. Energy. Energy is also conserved. So conservation of mass, conservation of energy, and the momentum equation. There is our basic equations. And of course, we treat the fluid as a continuum. You are not going down to a scale where you have to look at nuclear physics. Of course not. So then you really need to have smaller than 1 micrometer. So of course, a continuum should be quite okay. Now the book goes on by first setting up or obtaining the equations here on an integral differential form, and then afterwards put them in here and make an integral form. That is something that should be avoided, in my opinion. You should, if you are using a finite volume, or a finite element code for that matter, you are using an integral formulation to create your code, then you should start with the integral form directly. I mean, when you have the continuity equation, yes, this is one way to do it, to obtain this one, and then take a volume integral of the entire equation. But you can just as well start with an integral formulation, no problem. So I don't like this. And the reason I don't like it is when you have it on this form, then you have the demand for any variable here. The density and the velocity vector, they have to be continuous functions. You must be able to create the derivative of them. You're not allowed then to have a sudden jump in velocity or density like with a shock wave. But if you have it as an integral formulation, it covers more physics inside one single cell. Then you can have a signal, velocity, density, that all of a sudden makes a jump, like you would in a shock. And that's quite okay in an integral formulation, but it's not okay, it's not valid with a differential equation. So my point is, if you are using finite volume, start with your basic equations on the integral form. It covers more physics, so start directly with it. Of course, when you now are about to write project, master, reports, who are you writing for? What does the reader know of fluid mechanics? Well, you should think like this. You write to your colleagues in the class here. So the reader knows just as much fluid mechanics as you do. Hence, you don't start your report or your master by deriving the Navier-Stokes or the continuity equation. Everybody knows it. The reader knows them already, so you just put them up. This is the form that I'm going to use these equations and try to solve them. So you just put up the integral form directly. End of story. The reader knows them already. So don't do that mistake by starting too low, too easy. So here, a lot of equations. And the derivation of the Navier-Stokes, 3-dimension, rather boring. So of course, just skip all this. Also energy, really boring. Newtonian fluid. And then he does it again, but now on an integral form. So this is the point. Here is where I would start. So here you have an integral form of the Navier-Stokes, of the momentum equation, if you like, and the continuity equation. So start here. Much better. Okay, we can take a quick little example. We have the steady one-dimensional advection diffusion. So the equation then looks something like this, but not partial, it's ordinary differential actually. rho, no, not rho, only u phi equals d dx of viscosity and then derivative dx. More or less this generic form. Typically here they use a large gamma for the diffusion coefficient. Here I just use the viscosity directly, hence the unknown, the generic unknown phi then has to be a velocity. It's a sort of trick to linearize this term. But now you see if the phi was the velocity u as an unknown, non-linear equation. But we sort of say that we know the velocity u here, so it's only the unknown phi that we are focusing on. So this is the equation, and now take the integral of this equation. And here, this advective term is written now on a conservative form. You have the derivative in front of it. So that's then very convenient when you want to do a space integral. All these derivatives, they just disappear. So we will be left with just the parentheses here. But it's a question of the boundaries. So now we have to create a discrete world. So the standard notation is the center point P that we are focusing on, and then we are talking east, west, and north and south. East and west. At these locations I will have my unknown phi. Then I construct my volume, a small little control volume, and here I choose the midpoints. So this is sort of my control volume around my focus point P. So this is now my control surface. Then when I do this volume integral of the equation, I'm going to need the values here on this on the controlled surfaces. I'm going to need the values here on a small eastern wall and the west wall. So this one will now become something like this. It will be u phi. Let's see, positive to the right, so it has to be east minus u phi west. And then on the other side, we will have this parenthesis. Same way, viscosity, and then a derivative. d phi dx on the eastern wall, viscosity d phi dx on the west wall. So now it's a question. I'm going to need the value phi at these locations, but I don't have them on, in these locations. I have it only here in the center point P and the large east-west points. Also, I'm going to need a derivative located east and west. So how can we do this? Well, if we say something like the phi is constant inside my control volume. That's a very simple formulation. Phi is constant inside here. And then a different constant on the next volume. Well, what's the value on the boundary then? It's sort of not defined. Not to mention these derivatives. So if the phi varies like this, depending on which volume you are inside, then you can't really tell neither the value or the derivative on the surfaces. So phi equals constant inside the volume doesn't really work. Okay, we go to the next level and say linear variation. He may vary linearly inside the volume. Linear. Okay, what we get? Then we will have phi on the eastern boundary here. Then we just take the average, of course. 1/2 of, what will it be? Phi east plus phi center point. Same with the western point. And for the derivative, for these guys, well, we are going to need d phi dx at the point east. We then approximate him with phi east minus phi center point divided by the distance delta x between them. Actually, these delta x's, they may change from place to place, so in general, yes, we need an index for it. So you see, the linear variation helps us formulate whatever we need to obtain our algebraic equations, given the phis at certain points. And yes, of course, it's very, very similar to the finite difference world here. But the thinking is a little bit different. If you have a rectangular cell system, delta x is constant, you will obtain typically the identical equations as you would with finite difference. We can continue this example after the break. Any questions? Then we take a break.